and here we go. So today we have this last tree of week 6, middle of linked list, maximum depth of binary tree, and contain duplicates. So also, like, if you're not adding the Google Calendar to say like catching up with like PLDs, you can find it in like either welcome channel or announcement, and just add it to your Google Calendar, so this way you can check each PLD when and what LeetCode we are solving. So jump into this one, the middle of linked list. Let's read it and see how we can solve this one. Given the head of singly linked list, return the middle node of linked list. If there are two middle nodes, return the second middle node. So example 1 2 3 4 5, output should be 3 4 5. So you're gonna return from the middle. Azu, your mic is open. You have a background noise.
Sorry.
It's okay. So explanation: the middle node of the list is node 3. Okay, we should return this node. But if the linked list is even, then we should return, since the list has two middle nodes with the value 3 and 4, we return the second one. So in this case 3 and 4 are the middle, so we're gonna return the second one. Okay, what do you think, guys? How we can do this? What's the efficient way to do this? I already see some hint in the chat. How we can do it? What will be the easy way to do this? Any suggestion? You know.
We can use Floyd's algorithm with a little adjustment.
Okay, can you explain that how it will work, Ningas?
We essentially have two pointers, one moving twice as fast as the other one. And then essentially when the one moving fastest gets to the end of the list, it would mean that because it's moving 2 times as fast, it will mean that when it reaches the end, you're at the halfway mark of the linked list, because the other one will be 2 times behind it, or essentially at the halfway mark when the other one reaches the end.
We can try that. I think it will work. So 2 pointer, one fast, one slow, and we're gonna keep going through the linked list, and somehow the slow one gonna be in the middle element. Is that really gonna work?
I'm not too sure about when it's odd or even, but I'm sure halfway sure.
Yeah, I think
it works.
I think it works.
We can do animation and see. So how many nodes we have here? 3, 6, 7, 8, 9, 10, 12.
That's 11. Okay, 12. That's 6 times.
So in this case, the middle one. Okay, let's do one case with even and one is with odd. So in this case, the middle node should be this one. So 5 from, or this, wait, 1 2 3 4 5 6 7 8 9 10 11 12. So this is even, so it's gonna be both these two. So 5 on the left, 5 on the right, these two are the middle, and they say if there is 2 middle, we should return the last one or the second one. So in this case, we should return this node. Okay, using the one pointer slow, one is fast. Okay, let me see. Just post link if someone don't know this one, this algorithm. Here's the link. It's called Floyd. Yeah, exactly like the GIF. So the idea is like I'm gonna have one pointer slow, one is fast. Little fast with the red. So this one gonna jump like twice. This one gonna go just once. So the idea is like the fast when it's gonna reach the end, the slow gonna be in this one. But is that true? Let's check it out. So we start from the head, the slow do one step, then the fast do 1, 2. Then again we loop again.
It's gonna be at the 6th.
Then the slow do one step, and the fast do 2 step, 1, 2. Then slow do one step, then the fast do 2 step, 1, 2. Then 1, then 1, 2, then 1, then 1, 2, then 1, then 1, 2, but it will stop here because there's, so the loop gonna stop here because there are no more node. So it's like the condition if the next is, or like the next is none, we should stop the loop, and we can return the slow because it is on the target, which is perfect. But what if the node
So
have...
can you try for odd?
Yeah, that's what I like. What if it's have only one? So in this case, it's gonna be this one, and we're gonna remove this. So if it is an odd, it's gonna have 3. Yeah, so this is the middle one. Let's try it again. So one step, 1, 2, one step, 1, 2, one step, 1, 2, one step, 1, 2, one step, 1, 2. And because there's none, the next of the last node is none, we're gonna stop the loop and we're gonna find that this is the middle. Amazing. Wow. Okay, how we can write this code? Or who does have any question about the problem or the solution suggested there? So if no question, like if you have question, don't be shy. If it is first time you are here, welcome. Just grab the mic or write in the chat your question. We'll be happy to answer. Okay, no question. I think it's very clear. Now, how do we code this? What is the start? Declared pointer. So we have slow and we have fast, 2 pointer. Any help? What's slow gonna be?
I think 0.
So
Slow
the
has
head.
to be node next, right?
So
yeah, the head, yeah.
Yeah, before we go to the loop, so slow gonna be head. So they're gonna point on the first node, which is head.
Okay.
Now we want this gonna be a loop, right? Each time it loop, this gonna be moving, this gonna be moving. Now let's say we loop start. It can be while loop x. Let's say we don't know condition so far. So this condition x is like this loop gonna keep going as long this x is true. But let's maybe focus now on the condition or like the code itself. Then we see what is the condition to stop the loop. While fast and fast next also work. So while fast and fast next, but why? While
the fast
fast.
next should be true, because the it's not fast. The last one in the list should be
Should be false to stop.
yeah. Yeah.
So like when we're doing simulation, we notice that slow gonna be here and like the next gonna be here. Now I don't want this to loop again, which mean the condition that I have in while should be stopping me. But if we did fast in this case is gonna be but like it's hard for me. I'm not sure, maybe you guys it's easy for it to work the condition of while before writing the code here. Like for me it's always easy to write the code, then I can see how it's the condition gonna be.
Okay.
Let's say let's keep this as a dot right here, right? And let's just go with x, a condition x. We don't know what it is, but we will find it after. Now this we said we're gonna start here, right? What we're gonna do? What will be? We need to move this slow one step and the faster two step, right? So slow.
Yes.
How are we gonna move slow one step? What to do?
Equals slow dot next.
Slow. That's next. Okay, that means slow gonna go to the next node. Okay, here's it. Now what about fast? Fast. Is it fast? If we did fast dot next, right?
I think yeah.
So if we did
Yes,
fast
boss.
dot one next, it's gonna go like this. If we add another next, it's gonna go like this. So this is what we want. Now if this loop again second time, what's gonna happen? It's gonna go again one step, two step. Loop again, one step, two step, one step, two step, one step, two step. But in this case I want the loop to stop. Now if it didn't stop, what's gonna happen? This gonna be one step and this gonna be two step, but it's gonna give error, right? Because there's in the next of this, if we imagine this is the next right here, the next of the last node is none, right? So when we're gonna do this line fast, when it's gonna be here fast of next, that next it is none. So we can't do that. So then like is it fast next? That
No, I think you're making a mistake. Sorry, it's supposed to be at the last place. Yes, it's
Right
supposed
here.
to be like
Okay.
no. Go back. Move the pointer again. Move it. Yes, that's where it was before. No. That's where it was. Yes. So
Okay.
you move two times.
Okay, when this one was here, it was here.
Yeah.
No. Yeah. Exactly.
Okay.
Like this. Yes.
So
yes.
here it is in fast, so I need to check fast next. If fast next, which means this is equal to none, it should stop.
Yeah. That's
So
why
now,
we need
Correct.
yeah,
to check in the
now it
while.
makes sense why it's fast next here.
Yeah.
Now we can do fast next, because it's like saying, hey, this loop is gonna keep going as long there is a next node is available.
Yeah. We need to check also the current node.
The fast.
Need to check
Yeah.
also for.
Yeah, I think you check
next
fast
to
before you check
Yeah.
fast next.
Okay, now why are you gonna check fast?
Because in
What the error can cause if we didn't do fast? While fast next.
Sorry,
Fine,
can you
fine.
try for even cases? For even
Yeah.
cases and see.
okay, for
The
even
even
cases,
cases. Yes.
Yeah,
Oh, okay. So in even cases can be
the fast should be known.
okay.
In,
Let me shrink this a bit. So in even case gonna be like this, and let's say this is the middle, and okay, let's start from beginning. This one gonna move 1 1 2 1 1 2 1 1 2 1 1 2 1 1 2 1 1
two.
2.
So
So-
the fast is equal to none in this case. No.
1
The
2.
Exactly.
wow.
Exactly.
the
So
current
that no
fast,
Yeah.
so the fast
Yeah.
is known. Yeah.
So the last time, yeah, you're right. So when we're gonna go
why.
fast 1 2, fast gonna be equal none.
Yeah, and when a
Hmm. We need it to stop. So
yeah.
if fast equal, so when we do while fast, it's like saying, hey, as long fast is not equal none, or like none is, or like fast is also a valid node, keep this loop going.
Yeah.
Okay, now it makes sense. And I guess at the end we're gonna return the low, right? When
Yeah.
the loop finish. Return low. Okay. Let's see.
Low or slow?
Oh, slow. Sorry. Slow. Okay. Run. It will attempt none next. Oh, it work. Submit. Submit. Good job, guys. Nice work. Okay,
I can't see.
64.
Oh, nice.
Nice. Okay, not bad. Let's see. Let's ask first who have any question about this problem or the solution or the code. The code, like the code itself is Python, but you can do this with any language. For example, let's see this solution with C. Convert this to C. It's gonna be long, so don't be scared. Oh, it's actually not long. It's that short. Yeah, so
No, it can't be long. It's short.
Yeah.
Yeah.
yeah, so fast, slow. Then you check if the fast is null, fast next is not null. Then you move slow next, fast next, fast
It's
next.
the same
then you return.
lines. Yeah.
Yeah,
Same lines of code.
It's same thing. Okay, I'm surprised. Okay, now we can go to the second LeetCode, but before that, let's check some.
Try pasting that C example there. We see the type.
This one.
Yeah.
Do I test it in LeetCode?
Yes. Try testing it, and then we see how fast it is.
Oh, the speed. I think C gonna beat Python for sure. So this one is Python. Now if we take the C, not sure if it have the same structure. Let's see, this node middle. Okay, it's same structure. Run.
No, you need to well,
Yeah, because they have it built in.
okay.
Submit.
Mate.
Oh my god.
Whoa.
Oh my god.
Yeah. What is that?
100%. Wow.
My
I mean, it makes sense, right? Because
It's converted to
Python is
the
built
same.
on 100%.
We beat everybody.
Past everybody.
Wow.
With the help of AI.
Yeah.
Now we are truly using Floyd Mayweather's algorithm.
So with Python, it took 35 milliseconds, but I cannot seem to see what is the time actually with C.
It's 0 milliseconds, so
Oh.
it's probably microsecond or
This is
nanosecond.
blazingly fast. Blazingly fast.
Yeah, 0 milliseconds, so it's probably like microsecond.
Very close to the computer architecture. It's very fast.
Okay,
C
Let's,
is the goat.
let's jump to this one.
Mhm.
Second LeetCode is maximum depth of binary tree. This we did it before during the topics we were studying beginning, but it's okay, we can do it again, and it's gonna be the same as we do always with binary tree. We're probably gonna do diffs or bfs, but let's see what it is about. Given the root of a binary tree, return its maximum depth. A binary tree maximum depth is the number of nodes. Okay, give me a second, please.
Maximum depth. Anybody have any ideas of what we're gonna use here?
Sounds like a recursion.
Yeah, actually. I think we
Come
could
back.
use.
I'm sorry, guys, for that. Okay, what?
We just need to find the maximum height. I think like it is the same idea as finding the height of a tree. So it is the same as finding the maximum depth. So
Yeah, go ahead. What did I miss?
okay. So can you just like zoom in on the prototype of the provided function max depth? So we only have one parameter, which is the root. So I think like we need to check first as our base case. We need to check if we don't have root, then the maximum depth is 0. Otherwise, we need to check if the tree has a left child.
Is the tree have what?
By the left child, and then adding 1, and then we need to check also for the right. Okay. So
Okay.
first, we need to have our base case. If there is no tree, in other words, the tree is null, so the depth is 0.
Could you read the question again?
Okay, let's read the question. I'm sorry, I had to leave for a second. Just a situation going on. But it's all fine. So the question, Abdullah, you have echo. So
I don't
given,
know why.
yeah, you probably need to do this setting voice. There is a what is it called echo cancellation. This may help. Enable it.
Okay. Okay.
Okay. So given the root of a binary tree, return its maximum depth. A binary tree maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So what they're saying is the longest path, which is, so this is the path have one edge. This path have two edge. This path have, I'm not sure if this, I don't think you can do this. I think it's from a binary tree maximum depth is the number of node along the longest path from the root node down to the, so from this root right here, so 2 gonna be the longest
Also,
path.
20, 15.
15?
Yeah, yeah.
Is it
So-
better?
We can do
Yeah,
like
no.
this?
Yeah.
Okay,
I think.
okay. So I guess we can do like this and like this. We can see the depth. Okay,
Yeah.
it's still
So
not clear. I forget it.
for the given tree, for this given tree now, the depth is 2, because like the root is at level 0, and the next node at level 1, and the next node to the next is at level 2. If we are starting from 0. So like if you just looked up Wikipedia, you will find that if the tree is empty, then the height is -1, and if we only have one node, then the height is 0.
Okay, see, so like you said, if the tree have one node, then the depth is 0. Depth is 0? That's what you're saying? If it
Yes.
have 2 nodes,
Yes.
it's gonna have depth 1.
Yes.
So it's like counting the edge, right?
Yes. Yes. Kind of.
Okay,
But
let's
like
see.
for me, the way I
Based-
understand it is like
Based on the LeetCode problem, based on the LeetCode problem, it says that it's the number of nodes. So one node classifies as like a depth of 1, not 0.
Oh, okay, I remember this.
the maximum, the number of nodes in the maximum depth. They say the number of nodes. Can you just check it up again?
Yes. This one?
And the actual question on LeetCode,
Okay.
like we need to find the maximum depth or the number of
So a binary tree maximum depth is the
maximum
number
depth is
of
the number
node.
of given
Okay,
the
so
root
the
of
number of
within
node.
it. Yeah, so it is the depth. No, like up above, given the root of a binary tree, return its maximum depth, not the
Yes.
number of nodes. It's maximum depth.
But they explain the maximum
So-
depth here.
Yeah. Yes. So actually, so here the maximum depth is the path from the furthest node down. Like if we have in this given tree, the number of nodes from the furthest node up to the root. So we have here the furthest node could be either 7 or 15.
Okay, so we have, how many depths we have in here?
Here it is 2.
2. So
Yeah,
like
it is
one.
going to
Yes.
like this, going like this. So the edge, right?
Yes. Yes.
Okay, so like there is 2 ways to like to calculate the depth. You can use the edge or the node.
There
So
are
like-
2 ways to traverse this tree, because
Like-
we have left and right.
Like notice here they say 3.
So I think here they counted the root
The-
node as 1.
The node.
Yeah,
so
they
like
counted the root node.
yeah. So like
Okay,
they
so
say
like
yeah, so like they say return its maximum depth, but they explain what they mean by maximum depth here. So they say a binary tree maximum depth is the number of node. You know what I mean?
yes,
Like the
I get it.
yeah. along the longest
So-
path. Yes, go ahead.
So basically, it's the number of nodes in that path. So in this example, it's 3, 20, and 7. It doesn't disregard either the leaf or the root.
Yeah.
So,
So like instead of, so this is just like a little bit different from Wikipedia definition. So instead of node at depth 1. So if we take this approach now, the node 3 is at level 1, the node 20 at level 2, and the node 15 either 15 or 7 at level 3. So we will get the same result, which is 3.
I see. Longest path from the root down to the furthest leaf. So you're right. There's like a multiple definition for the, like for example, the depth of node is the number of edge present
here,
in paths from the
yeah.
root node to tree. So
Here the definition of geeks for geeks, like it is quite similar to the definition of Wikipedia, but like according to the exact question of LeetCode, like we just need like to follow the requirement as like
yeah. Okay, let's
all
go.
requirements.
Yeah,
so like
let's go
we
with
just
this
need
one.
Yeah.
So, how we can do this? What is the idea, guys? By the way,
Okay,
I have a question first. Let's see if everyone understands what we're trying to do here. Or like, let me repeat just quickly. So, we want to see this node right here. We want to see what is the longest path, which is this one, and then count the node on it, and then return 3.
Yes.
Now, how we can do this? Yeah, go ahead.
Okay. My suggestion is, we need to check first. If we, as our base case, like my approach or my main idea to approach this problem mentioned before. So like our base case would be if we don't have if we don't have a tree, then this means like if the node is null, then this means we hit our base case. Otherwise, we need to recurse left and recurse right. And at the end, we need just to return the maximum of either the left or right.
So the first approach, I think, DFS, right? The recursion.
Yes.
Okay. Who have any other solution? If not, we can go with DFS, or we can try to do them both. Who have any idea or suggestion? Okay, we can start with the DFS. Okay, you wanna I'm not sure how to do this. Maybe give a link. You wanna explain how it works, Abdullah?
Okay. So first we need to check if there is no root.
Okay.
Like this is our base case.
Okay, so base case gonna be if not
If the root is null or
if the root
is none, then we return 0.
then return 0.
Yes. Otherwise,
Okay.
if I have a left child, if root left,
If root left,
then I recurse left. So I would say I need first to declare 2 variables up above at the very beginning, left.
That first statement, what have you written?
this one.
Of if I have a left child, at the very beginning, I need to declare two variables like left equals 0 and right equals 0 for instance.
Okay, right equals 0.
Yes. Then after the condition, after I have checked that I
Yeah.
have a left child, then
Yeah.
this means I need to recurse left. So I would say left equal
Left equal. Okay, let's say this function called
then
def max depth.
yes. Then here I need to recurse left. I would say I will call my max depth again, but this time I will give it, instead of root, I will give it the left child as a parameter. So I would say left, root left.
Root left. Okay.
Same kind of flow control for the right subtree.
Okay. Sorry,
I
I'm
would do the
lazy. I'm
same
gonna
for the
just
right
paste
subtree.
copy.
Yeah, exactly.
Okay.
And then at the end, I will return the maximum value of either the left or right. The maximum, yes, I think there is a built-in function in Python called max, yes. I would just return the max of left and right.
Okay.
But I think there's something missing. Anyone has, anyone can spot any
Yeah. I think something missing here.
shortcoming, any shortcoming
something-
in this flow?
Yeah.
Anyone can spot any shortcoming or like missing parts in this flow?
Yeah, I think the addition. There's no addition.
Addition of 1.
Yeah.
So we
I
can-
would say one plus max here. Yeah, it is to say one plus. No,
Yeah.
and not at
Plus
the
one.
end. Like for the condition, for
Yeah.
the assignment for the left child and the right child, I just need to say one plus.
One plus.
Then the function call. Yes,
Right.
yes. Because I need to update my counters for the left and right.
Okay. Now, let's see.
And
Is this all? I think that's all.
Yeah, I think.
If not none. If it's equal none, then return it. Okay. Do we need to do this here? Does it work like this?
Finish it after.
but like this way, if I didn't declare two these counters for the left and right, that is scope, because like they have to be in the outer scope in order to be accessible in the last statement, which is the return statement. So like you can just put them at the very beginning before checking like if the root is none, maybe.
Okay. But let's apply it on this one. See if it was working.
Yeah, let's like we're talking theoretically, so like let's get our hands dirty.
Yeah, but before we do that, aren't we supposed to launch the max depth on the root?
Come again, I didn't get that point. To launch the max? What do you mean by this?
Okay, so it's gonna launch. Okay, okay. Maybe. Yeah, it's here. So this gonna start. Okay, let's just keep going. Like this simulation. So it's gonna start on the root.
Follow this code flow on the whiteboard first before we can test it.
Yeah. So it's gonna launch on the tree.
So let's say first, let's imagine that we have only up to the level 2, which is level 9, and yes, up to this level. Yes, up to this level. So first we check if we have if root is none, which is false. If I have left child, yes, then I recurse by the left child and I call max depth again and I pass it the node 9. Then
Okay.
I will add a new function to the I add a new stack frame for the node 9, and then when I hit the node 9, I check again if the root is none, or like now the root.
Mm-hmm.
So I check if the node 9 has left, no. The node 9 has right, no. So I return the maximum of left and right, and this stack frame, the
Zero.
left and right are 0.
So this
So
can
I
return.
will return to the column function,
we
which
need
is
to do
node
plus
3.
one here. So because this one needs to return
The plus 1, it will return 0 to whom? It will return. Yes, you are right. I think we need to add 1 here. Yes. The maximum plus 1. Yes, maximum plus 1,
Okay.
I think.
Okay, let me try to
Maximum plus 1.
do simulation of the code on this graph itself and see how it goes. So we have left and the right, so we create variable left and the right,
Yes.
and we put 0, 0, and then we go to here and we check if the root is equal none, we're gonna return 0. In this case, we are starting with the root equal 3. So our root is 3.
Yes, our root is
so
3.
this it's not gonna enter here.
Yes.
Now the root left,
will go left.
which is 9, is exist.
Yes.
So it's gonna enter here. Now in this variable
Yes.
left, we're gonna have the value of max depth, which is this
Yes,
function
so-
itself. So it is recursion, and the return
call
of
it again.
it. The return of it, we're gonna add to it plus 1. Now this function itself is gonna launch on this 9. Now this 9, it's gonna
Can
go.
I share my screen?
Yes, or you can. You wanna what's it called? You wanna link to this Excalibur?
Come again?
Do you wanna link to Excalibur?
Link what?
Do you want this link for
Is this no application?
for this Excalibur, this website?
Not Excalibur.
Okay, let's do
I think it is
something.
the whiteboard.
Okay, let's do something. I will finish this simulation, then
Okay,
you
okay.
can present your
No
screen.
worries.
What do you think?
Okay. Yeah.
Okay, so
totally fine. Right.
yes, so the left variable is gonna have max depth root left, which is this function itself. So it's called recursion on this. Now this recursion is gonna start again with the same code, right? So it's gonna have left 0, right 0, and then it's gonna check if the root is none. It's gonna be not none because it have 9, and then it's gonna
Yes.
check if the root left is exist. If we can notice here, the root left is none and the root right is none, so it's not gonna enter here and it's not gonna enter here. So what it's gonna do is gonna return max left and right, which are there 0. So this 9, it's gonna return left and right. So max of left right 0 0 is 0. So
Yes.
it's gonna return 0 to the left
To the
that we
column.
launch in 3, right? So left in
Yes.
this case
Yes.
is gonna have 3. It's gonna have 0. So it returns
1.
0 here.
Yes.
0, right? Now the
Yes.
left in the root, it's got 0 in this variable, and it's add to
Plus
it
1.
1 plus 1 here. So
Yes.
left here is 1. And then the same gonna happen for the right. This gonna return 0 to this, 0 to this, but this gonna add to it 1, so it's gonna be 1. This gonna add 0 plus 1, which is 1 and 1. This gonna also do the max of them, which gonna return 1 to this, 1, but this tree is also gonna add 1, so it's gonna be 2.
It is 2. So this is why we need to add 1 at the very end.
2. Now this
need
root
to add
tree,
1.
this root tree, he gonna do max between left and
And
the
right.
right. Or which gonna be
Which is
2.
2 and 1. Yes, this is why we need to add 1.
Yeah, we need to add 1 here, so the root, because the root is not counting itself. But if we add 1 here, we're gonna ruin this.
Someone here suggesting we need to initialize Sabah. We need to
Initialize the right and left with 1.
if the tree was in the very beginning it was empty, then we should not return 1. We should return 0. If we initialize the left and right with 1. If we are given an empty tree, then we will just return 1, which is not the right result because the tree is empty.
If the tree is empty, it's actually gonna get trapped in the if root is none. It's gonna return 0.
If we initialize root left and right with 1, then we will not hit the condition. We will not hit any condition. Like all of the condition will evaluate to false. Then we will return the max of left and right. And since left and right are initialized by 1, we will return 1 for an empty tree.
If the root is none, it will get trapped in the first if condition. If root is none, it will return 0.
Yeah, you are,
Line 3, yeah.
We can try it, right?
you are right.
Try it
Yeah.
That's
So I think
interesting.
Sabah's
That's
suggestion,
interesting.
Sabah's suggestion is right. We can initialize the left and right with 1.
So what about if you have one node, just one? That's the only root, just the root. That's 1, right?
Okay, if I have
It's gonna
only 1
return-
node,
It's gonna return 1.
1.
if I
okay,
have
nice.
only 1 node,
Only
I will
root,
return
just
1.
the head. Yes.
Yes.
I think so.
Yeah.
Okay, I see also
Okay.
some solution.
Give it a
here.
go.
+1, return max left. This work, I checked. So this one it work. Wait, so with the 0 work? But I think
If we initialize left and right by 0, we need at the very end to add +1. If we
okay.
initialize them by
Yeah, I think this one work
add 1 at
because
the very
you
end.
don't have this. You don't have this. This F. That's why it work, I think.
So
if you have
that,
F,
the
it's different.
difference between those two codes is that you're catching that root left before it gets there, and the code that Mina sent, you get to that null node, then you return 0. But here you're trapping it in, for example, in 9 instead of reaching to 9 next.
So his code is always gonna add 1 even if this node doesn't exist. But our code only add 1 if this node exists.
Yes.
Yeah, the order matters, especially
Yeah.
when it comes to recursion.
Okay, do we keep trying this one? Let's see one if it's gonna work. Just experience.
Give it a go.
Left is 1, right is 1. Now if the root is none, it's not gonna enter because the root exists. If the root's left, it's gonna go here. It's gonna launch max depth. Max depth, it's gonna return 0.
Right.
It's gonna return 0 to here. And then this one gonna add 1 to it, so it's gonna become 1. Oh, sorry, it's return 1, not 0. It's gonna return 0, right? Because the left is... Yeah, because it's gonna get 1 from this. Because left and right are 1. So this gonna return 1 to this, right? because max depth gonna enter on the left, on the right, and because they are, wait, I think I'm confusing myself. Let me start again. So this gonna call left on and right, left and the right, left and right. Now the left max depth function is gonna call root left and root right, but because because they are none, it's gonna return 0. So this gonna return 0 to this, and this gonna return 0 to this. Now this one itself, wait, oh, it's not gonna call this because there's no root left. Yeah, sorry, confusing myself. So this gonna call when tree gonna call 9 with this max depth, the max depth gonna stuck here. No, wait, where it's gonna be stuck? So it's not gonna enter there, and it's not gonna enter here because it doesn't have root left. It's not gonna enter here because it doesn't have root right. It's gonna return the max of 1 1. So this gonna return 1. Okay, now I see it. So it's gonna return max of left to right, and they are already 1 1. So max of the 1 1 is 1. It's gonna return 1. Now here's the confusing part. Now this can return 1, right? In this line, in tree, and the node tree is gonna add another 1 to it.
Yes. So
it's
the
gonna
height
become
or
2.
the depth of the left subtree is 2. Yes.
Which actually is 1.
The depth.
There's 1 edge
No.
here.
No, it is 2.
We are counting
Because
the
if you refer back to their example,
we are
they
counting
are
the node.
counting.
Oh, the node.
Yes.
But
yes.
Okay, I see. Yeah. So 2. So it's counting 3 and 9. Yeah.
The same apply for the right subtree. So when we hit the right subtree, so then we will recurse again to left and right. So since this distance is 2,
right? So this one gonna return 1 to 20, and then 20 gonna add to it 1, which gonna be 2, and then this gonna return 1, and 20 gonna add to it 1, so it's gonna be 2, and then this gonna return the max of them is 2, and then this gonna add to it 1, which is gonna be 3.
Yes.
And this we gonna return the max of them, which is 3. Okay, I see.
Yes.
So actually 1 1 did solve the problem.
Yes.
Can I make a suggestion?
Yes, please go ahead.
You may make left plus and equal and remove plus 1 from the end, and it will work.
So like this?
Left? No. Return back. Left plus equal, and remove the 1 from later.
Like this.
Oh, you already have 1. You're just adding.
Oh, okay. Yeah, because they are adding 1, because they're gonna return.
Already there.
Okay, that's smart. Nice. Okay, let's test this. I am ready. Thank you, Abdullah, for this beautiful solution. Let's see how we can code it.
All collaborate on this. So thanks go to the whole people who are here in this session.
Fixing this bug. And thanks to Mina Midhat for this optimization. Okay, how we can think something is missing, right? Self. If not root. Yeah, we can do if not root here. They're the same. If not root, it's same as saying if root equals 0. Is that all? Let's see. Run. Oh, max depth. Yeah, function name. Run. You have attempted to run the code to zone. Please try again few seconds. Okay, let's wait a few seconds, guys. That's enough. I think it's enough. Let's run again. Okay, it worked. Nice. Let's submit. 60%. Nice work. Nice. Good job. That's really nice. Any question, guys? Who have any question about this problem or something not clear? If the recursion is something you are struggle with, we did like a PLD session about recursion. You should check it out. Let me post the link. Through all this, where is it? It is somewhere here. Recursion. This one. We did go in the recursion in details. It will help a lot. Now, do we jump to the last LeetCode, or you wanna try other solution with this one? I think this one is simple.
Yeah, actually,
case.
I've been thinking.
Yes, go ahead.
If we could do it in a normal loop instead of recursive approach.
Yeah, we can try that. That will be BFS. So we can use like stack. Can use like stack or like DQ, right? So if we want to do it
the
with
G structure again.
Your voice is cutting off. With the BFS, we actually did this one before with BFS.
You did it? Okay, nice.
Yeah, we did it in one of the PLD.
How did you do it in BFS? In a level order in traversal?
Okay, let me remember. So it was a stack. We had a stack, right? Say a queue. And we put this node. Okay. What did we do?
Remember, we have to keep track of the ones that we visited, as well as we take them out of the queue, right, of the visited node, and then we investigate. Oh no!
Oh, that's one. Yeah, I thought something similar. Wait, I may find it here in submission. Which was probably this one. Okay,
I think
here one of it.
We need to have two variables, one to hold the left subtree and the second one to hold the right subtree, and two counters, one for the left subtree and one for the right subtree. And on each iteration, we need to either to go left and right, and then increase our counter for the left and the right accordingly if there is any node. I think. What do you think to give it a go?
Yeah, we can try. This one was one of the solution that we did the other time. I think we did many. let's see this one. This one was using queue, and the first one we did it was recursion. Okay. Okay, you wanna explain your solution?
I'm not quite sure about it, but like I'm just thinking out loud. So my idea is we need to keep track of the left subtree and the right subtree, and as long as we have left subtree and right subtree, we need to reassign the variable and to increase our counters for the left and the right accordingly. So if we started from there, if we started from the root, so first we need to initialize our two variables for the left tree and right subtree with the root.
So we're gonna use like a
in our loop, as long and in the loop, as long as either of the left subtree or the right subtree are true, in other words, like there is a node, then I need to reassign them to go either left or right if there is any node, and I need to increase my counters also. And then after I finish from the loop, I need just to return the max of the two counters for the left or the right.
Okay, let's try to code it. It's similar to the one that we did, but we did this inside a tuple. It's like we did this inside a tuple.
Yeah, you need the tuple in order to store the depth, right? That particular node was at.
So like, let's say we have a DQ, a Q that we're gonna put root, and 1. And 1. And then we're gonna keep looping on each node, and we're gonna increase this number. It's okay, it lost the thoughts, but okay, let's try it. Let's create a queue. So we have a queue like this. We're gonna put inside the queue 3, not 3 plus or like, let's say 1 in the tuple. 3 1. Then we're gonna pop it out. We're gonna pop it inside the while loop, and what we're gonna do is we need the next of this, so the left one and the right one, we're gonna add them to the queue, right? But we are adding them to the queue. We're gonna get this number and add +1. So we're gonna keep doing the same for this. When we're gonna pop this, it's gonna have 21, 2. And then when we're gonna add this, we're gonna add +1 to this 2. So this is one of solution that we did before to keep track the levels. So we're gonna enter the queue while queue, which means as long as there is node inside this queue, we're gonna keep looping. Now I need to pop this. Wait, I need to do it in tuple. So I need to pop this 3 1. So the number 3 is gonna be the node, so node, and 1 is gonna be the level. Now how to pop this from the queue? this function have q left or pop left, but we need to use pop left. I forget why, but pop, if you use pop, it's gonna pop the last one from here, but if you use pop left, it's gonna pop from this side, from the right side.
That was the reason. Remember when we
Yeah.
popped it, it was just coming out wrong.
Yeah. Now we have node and we have level, right? So we did pop this. We have access to this node tree and we have level 1. Now we need to add the node next, node left and node right. So how we can do that? Append, right? We need to append them to the queue. So but node pop left, how we can append queue, append node left and level +1. Now when we do this, we're gonna have in the queue 9 2 9 2, right? The node 9 right here plus level +1. Level we get it from here because we extract this tuple to 2 elements. The first element go to node and second element go to level, which is 1. Okay, and we're gonna do the same thing for the right side. Q right and right. Now what's happened here is we add another element which is 20 and the level 2.
Yep.
But we probably need to check if node rights exist.
Yeah, I was gonna ask that. Do we not check existence
Yeah.
before we access?
So if node lefts exist, because we don't want to add something to the queue that doesn't exist, or in that case the while loop is gonna keep looping. If node right exist, we can even add another check here. If, or like we can do it here, if not exist, or we don't have to. Like, do we guarantee that the node gonna always exist?
I believe so. From the root, right? We start off with the root, and then after that, within the while loop, the only way we add things is if they exist. So we guarantee that the queue will always have things that exist.
What if it was only one node? Probably gonna give error here. Because it doesn't have left or right.
How do you mean?
I'm just thinking maybe if it was one node, we're gonna add it to the queue.
Yeah.
Then we're gonna pop it, and then we're gonna check if node left, but it is none.
Yeah, then it won't add it to the queue append.
Oh,
the
okay,
node
you're
left.
right. Yes. So
You
the
just have
node
to
left is
indent.
yeah. Okay, so this makes sense. And this loop gonna keep looping on all elements, adding them one by one, and just adding this +1. Okay, what's gonna be now at the last element? Now the last element gonna be in the Yeah, so the last element is gonna be in the queue, have the highest level, right? Because if we keep going all until until the queue is empty, doesn't that mean the level gonna be the highest?
Yes, but the problem is the queue will dequeue everything, so we won't essentially be keeping track of that last element. We might need, as Mina said, a variable outside of everything that just stores the maximum level.
Okay, but we can still have access to this variable.
No, it's only within the loop.
Okay, so should we have,
I've been thinking.
say 0,
Yes.
and then
Don't we have access to node and level from outside?
I think so. I think we have access if
I think we can just return level. Yeah.
I thought the scope of node and level was just within the while.
we can
That's
try
not
it.
Oh my lord, what language are we in?
So while 10 and what's I'm doing while 10? Let's say while, yeah, let's just while true.
This brings back memory to a simple shell. While 10, while
level 5, right? And then I'm gonna break, and then print.
Hey, semicolon from where now?
Oh no. Okay, so if we don't have access, it will not print, right?
Yeah, I'm expecting a nasty error.
Okay, this print.
Oh lord.
I actually forget.
Can I?
Yes, go ahead,
Python
please.
is a motherfucking language.
No, the thing is, this case and that other case are different. Are you aware?
No. Isn't this
Because
return
here you're
level
not
is
increasing
inside?
it. You're not increasing the memory here. I think you're just adding one to it. It's not increasing in memory. If I'm not mistaken. Correct me if I'm wrong. I don't know. Okay,
so
you added. Okay. The pop left. Yeah. The pop left updates it. Excellent. Thank you. Excellent.
yeah. Yeah, so like this, so like if someone having hard time to catch up, is like there is this code which inside this while loop, right? So our idea is like wherever this variable we declare inside the while loop, we can't access from outside. But we just forget that you can actually access it. So we can just do return level, and then we're gonna have the highest level, which means the last node that gets pop out or like pop left. Okay, let's see. Yes, go ahead, please.
I've got a
If the
question.
root is just one.
Yes, go ahead, please.
If it's just one node, what happens?
Yeah, we can
Yeah,
try
actually,
with one
and
node.
you are increasing the level twice. Like if I have two nodes, if a node have two children, like left and right, you are increasing the level twice.
Where?
You are checking if the node has left, then you append node left, and then you are increasing the level by 1. You are incrementing the level. And if the node also has a right child, then you append the right child, and then you are also increasing the level.
Okay.
And
not
since
necessarily, it's not an assignment. It's
to
it's not an
increment
assignment.
the level at either children, because this way we will increment the level by factor of 2 instead of like just assuming that if the two nodes at the same level, we need to increase only at one child, not.
I see what you mean. Let's do
Not
a small
necessarily.
test.
The level is not being assigned until the next iteration, if you know what I mean, until the next thing is popped out. So what he's essentially doing is just if the level is 2, for instance, if it has a left, it will add 2 plus 1, and then that will be its new value, a new value entirely. And then at the if statement for the right, if that exists, it will be 2 plus 1 again because the level isn't getting reassigned. If that makes sense.
Yeah, it makes sense. It makes sense.
Yeah, I hope it's clear for everyone. Like, if the level here is equal to, and we did this operation, the level itself is still equal to. And when we're gonna go to the next line, the level is still equal to. So we're not changing the level. It's just like picking this value and adding to it 1. And the result is what we sending to this append.
Yes. Yeah, I think yes. It makes sense. It is legit. But like, what about the for the time complexity? It is totally perfect. But what about the space complexity? Because now we are introducing 2 data structures. I would say 3 data structures. We are introducing the list, and we are introducing tuple, and we are introducing this data structure of DQ. So like for the space complexity,
I'm not sure about space.
So like we can have the same logic.
Yes.
We can have the same logic with only list. But we need 2 additional variable. Since we are dealing with a queue, we just need 2 integers, when to count for the front and when to count for the rear. And by this way, whenever we enqueue, we increase our rear by 1. Whenever we want to dequeue, we increase our front by 1. So our rear and front can start by 0. And whenever we want to enqueue, we increase our rear. And whenever we want to dequeue, we use our front variable. And this way, we will maintain, like I would say, to the best of my knowledge, best performance in terms of space and time complexity.
How much space complexity is gonna be?
What do you think?
2 to the power of n, I think, depending on the height and the depth. So the deeper we go, the more things we'll need to store at one go. You know what I mean?
Or to
if it's a
my idea
string.
is
yeah.
My idea is we don't need a tuple data structure, and we don't need a queue. We need a queue, but like we will have a queue like behavior with only list. But we need to introduce 2 variables, one for the front and one for the rear, in order to simulate the same behavior of the queue.
So how much for the space complexity gonna be?
I'm not quite sure.
I think this one, how much space? Because it will be nice, like, to compare the time complexity and space complexity. I think the DFS is best solution, right?
Yeah, the DFS it is totally fine.
DFS. The DFS, the one we did in the first, the recursion one.
The DFS, we also have a space complexity because every recursive call, it adds a new stack frame to the stack, because we on each iteration of the recursive call, we add a new function with new variables to the stack. So each recursive call adds a new stack frame to the stack. So like with the recursive call, there is also a concern about the space complexity. Like maybe I'm just like overdoing this thing, but like the solution is totally fine. Like the space complexity, it is not that big of a deal.
Yeah, but like the space complexity is gonna, like, each program has space complexity, right? Like any program has space complexity and time complexity, but it it will be nice to do a solution which take less space complexity and less time complexity.
So yeah, so if we try to reduce the space complexity, so we need to get rid of the tuple and DQ their structure. And we maintain the same logic, but like we just need to introduce two variables, which is front, like the same logic as here, but like whenever we want to enqueue, we will increase our two variables would be the rear and the front. So the rear to enqueue or to add at the end of the queue, and the front to dequeue or to pop an element. Like here, this method is called pop left, right? So the front will give me value from the front.
I did ask ChatGPT about like comparing the BFS and the DFS. Let's see what's the difference between them. So space complexity primarily depend on size of the queue. In the worst case, the queue can contain all nodes of the tree last level. Thus, the space complexity is ON, where N is the number of nodes in tree. Okay, so the space complexity is ON. The time complexity is also ON, where N is the number of nodes in tree. This because the algorithm visits each node once. And the second application, which is recursion, the space complexity here determined by the recursion stack. In the worst case scenario, the depth.
Yeah, the second one, I think,
can be equal
the
to
space complexity is the height, where height is the height of the tree.
Yeah. So like in the worst case scenario, the depth of the recursion stack can be equal to the height of the tree. So this is like, I guess we're gonna always have the worst case scenario, right? Or not? No, not the case, because we're only looking for the outside routes, right? Or maybe? No. Yeah, forgive me. Forget what
we are enqueuing. I think we are enqueuing all the nodes, so I think it is also open, like for the BFS.
For time complexity.
Like yeah, it is fine. It's fine. Like.
Okay.
So I think the recursive approach and the iterative approach has the same kind of
space and but I would like to see your solution. Maybe you can write it and like send it to us in the chat. We can like go through it. What do you think?
Okay. No worries.
Yeah, let's see. Then we can compare and see which one is better in space. Maybe learn some trick how to optimize space complexity and time complexity. Now, because there's like 30 minutes left, let's jump to the last LeetCode.
Yes.
Contain duplicate. Okay, let's try to understand what is this problem. Given an integer array nums, return true if the value appear at least twice in the array, and return false if every element is distinct or unique. Nums 1, 2, 3, 1 true. Why true? Because there is 2, 1, so there is a duplicate. Nums false. Why false? Because it's 1, 2, 3, 4, all elements are unique. Okay, what do you think, guys? Each one of us try to solve this one, and then like 5 minutes from now we see the results of each one of us. How did they solve it? I can't wait to see your one-line solution. I already see Sabah probably writing this code in one line, or Nyangasi. Okay, let's see. TikTok, we're starting. Let me write the link. counter, collection. Now we're gonna solve this. By the way, who didn't understand the problem, like please just
Long
open
story
mic.
short,
Yes.
if I am allowed to participate
Yes,
again,
please. But you are always this is your PLD, you are always allowed to participate anytime.
okay.
And like you
long
can
story short,
yes.
we can make use of the dictionary. So like,
okay.
so we need to put each element in a dictionary, and as we iterate, we check if this element already exists in the dictionary, then we just return true. Otherwise, we keep working.
That's smart. So we're gonna keep looping on H1 and at the same time we add them to like a dictionary, and then if we find them second time we are true, still looping, we return false. Or like we
Yes.
return true as like there is the okay, that's smart solution.
Yes.
Okay, someone did it with one line, of course, Saba. What they did here, they use counter nums, most common. Wait, how this work?
Collections library, baby.
What is this? Collection counter.
Collections is the collection of optimized data structures. So yes, you can use the dictionary, but collections already does a lot for you. What the counters will do is it'll take whatever array or list you have, and then count how many unique elements they are, and then the function or the method, most common, will grab the most common.
Nice.
And then after that, you check whether or not the most common thing appears in the frequency of 1. If it doesn't, then it indicates that there's duplicates.
How do you even think of this? What is the key? Okay, there is another solution. Yes, go ahead.
When you use DQ,
the
you're
built-in
using the collections
function
library
into the collection, then it then the counter counts the current number on the iteration. Then I check the most common one. Like what is the first parameter one indicates for the method most common? What is one indicates? Like what would happen if I fail?
The number of returns. So if you put 1, it will only return the most common. If you return 2, if you put 2 or 3, then it returns the 3 most common. If you don't pass anything, it will return the whole list in order.
The one most common.
What about 0 and 1?
Sorry,
so
I didn't get this.
So it returns an array. Yes.
If I feed it 2 instead of 1, what like?
It'll return the 2 most common in order.
Okay.
The 2 most common. So like.
So
in my list, then it will return the 2 most common.
2, 3. Right. So
yes,
the most
in my
common
list
is 2. Is that what?
The most common is 1.
Is 1. That's
the most common is 1. Okay, I get it. I know.
So it's
the most common, and then I access the first element, which is 0.
What is this parameter?
So it returns a list of tuples, yeah?
Tuples. Oh, okay.
Yes, so you access the first one and then the first element of that. I guess second.
So it is array of array.
That's cool.
It's an array of tuples, where the tuple, the first one is the key, and then the second one is the amount of times it shows up.
Nice.
Frequency.
Like Python.
Let's see.
Python has everything set for you.
Yeah. It's amazing. Let's see this solution. So it did hash set.
Return value of the most common, like in order to investigate it.
And then wait, let me take it to Excalibur.
Yeah.
So
it's looking for any. Yeah, that's nice. It's looking for a collision. If you're trying to add something to the set, but it's already there, that would indicate that It's a duplicate and then stop.
Okay, so you create a set hash, you keep looping, and if we in the hash, so this is kind of same the solution to Abdullah. You're just using the hash, using set here. Else?
Yeah, it is quite similar. Yeah.
Okay. Okay, that's really smart. What else? What else, guys? What else?
Can you just print out the return value of the most common?
Print out the value of the most.
How
Okay.
does it look?
Okay, let's see this one. Then we do that. So this is another solution. What is this? Is you're gonna check the length of nums, and you're gonna create a set of the same number, so automatically it's gonna remove duplicates. Wow. And then you're gonna check the length if it's same. If the length is changed, that means there was a duplicate that got removed, so you return true. Oh, did you catch this one? That's really smart.
Yes, this is nice.
Wow.
It's neat, actually.
Yeah, so what's happening here is like if we have 1, 2, 3, 3, right? This is nums. We're gonna check the length of nums, which is 1, 2, 3, 4, so it's gonna be 4. And then we're gonna check it with another length of the same one. It just this time we're gonna put it inside a set. So we're gonna create a set. Let's say this is our set. Who doesn't know set? Set is like same as array. It just doesn't accept duplicate numbers. So it's all the elements inside set is gonna be unique. So if I transfer this array to a set, automatically it will remove duplicate number. That's what I believe. You can try it and see. So 1, 2, 3, 3, it's gonna become 1, 2, 3, right? Now we have this array and this one. We're gonna check the length of this one. It's gonna give us 3. We're gonna compare 4 and 3. If they are not equal, that means there was some duplicate that got removed, which means it's gonna return true. Wow.
From the that's nice. From the question, are we returning the value which is a duplicate or just returning true or false?
True and false.
Oh, okay.
Here is another one. I think this one also playing the same concept. I think it the set concept too. So create stamp and then you check the length. Yeah, this is one that's also the same. That's really smart.
I think the second one is easy.
Pac-Man is also doing the same one. Okay, you guys are so smart. Nice work. Hurry up. I guess that's all. That was the 3 LeetCode for today. I wanna thanks a lot Abdullah for jumping on PLD today and explaining his solution and contributing to this session. And everyone else, Sabah, Ningasi, everyone who type in the chat or open mic and talk. Today we finished the last session of PLD of week 6. So next week we're gonna start the week 7, and this is the list of the PLD we're gonna do. So as always, this is gonna be Tuesday, this is Wednesday, this is Saturday, and the last one we're gonna do it Sunday. If you're not adding this Google Calendar, you can find it to keep track with the PLD time. That was it. Clap for you guys. And if someone have question or something, please go ahead.
We're graduating to medium difficulty.
Okay, let's not forget this solution. Okay, let's check it out. before we end this session. So what happened here? You get the array, you create a list, you loop on each element, you add it to the list, and then if you find it again, you return true. Yeah, that's smart. So this is kind of the same as Abdullah and others. Instead of using hash map, you use the list. That's cool. Okay, see you next week, guys. Have a good night. Love you all.
Thank you. Have a good night.
Thanks for the checkup.
It's time for Nigeria and Ivory Coast, guys.